Hello, and welcome to the second installment of our Cresset webinar series. Today we'll be talking about using reagent databases to find the next move and accelerating lead optimization with bioisosteres. My name is Ray Lawrence, and I'll be your presenter for this series. During the session, should you have any questions, please feel free to submit them via the GoToMeeting chat pane. The Cresset team is monitoring and will be able to answer your questions as they are submitted. For today's session, we'll follow an agenda that'll cover, we'll do a review of the Cresset technology, we'll look at field points and how field points are used to compare molecules. We'll do a brief overview of Cresset's products and focusing in on using Spark for field-based bioisostere replacement. We'll also look at using Spark and the Cresset-provided reagent databases to find the next move. Cresset's philosophy is all about looking at ligands the way they are seen or experienced by the protein receptor. To do this, we step away from the 2D representation and consider a ligand as something that has a three-dimensional distribution of shape, charge, and hydrophobicity. Now, comparing molecules using the full electrostatic potential energy surfaces is computationally expensive, so we've condensed this information down to what we call field points, which are placed at areas of local extrema in these functions. Blue corresponds to areas where the electrostatics are negative. Red corresponds to areas where the electrostatics are positive. Yellow gives a van der Waals accessible surface area, and the orange field points are in areas of hydrophobicity. The size of the field point corresponds to the strength of the field at that point in space. The presence of a field point suggests that this is an area of the ligand which may form a favorable interaction with a protein receptor. It is noteworthy to say that just because a field point does not appear, it doesn't mean that there's no field at that point. It's simply that the field is not at a maximum value. So with Cresset software, we use these 3D field point patterns to compare molecules in a biologically relevant way, the way that a receptor would experience the ligands. For example, if we have a bound conformation of cyclic AMP with this field point pattern, and we have a synthetic analog that has an energetically accessible 3D conformation that has a similar field point pattern, then the receptor should see these two molecules in the same way, regardless of how similar or dissimilar their chemical structures are. This allows us to compare molecules at the bioisosteric level without bias. Going a step further, the technology can be used in the ligand design process for optimization or scaffold hopping, which is shown with the changes made to the middle molecule to give the molecule on the right-hand side. So we've chopped off a bit of this molecule. We've got a new fragment in place here, but the whole molecule bioisostericity has been maintained. We do these comparisons with 4 products. Blaze is our virtual screening application. Spark is used for bioisosteric replacement and scaffold hopping. Torch and Forge are both used for design and understanding structure-activity relationships. Torch is very much a medicinal chemistry tool. Forge is a computational chemistry tool, which includes additional functionality over what's included in Torch. First, we'll review how Spark is used and what it does. When doing bioisostere replacement or scaffold hopping with Spark, we want to be able to cut out a bit of the molecule, either central or terminal, and have the software suggest bioisosteric substitutions that can be made. In the case of rofecoxib, if we were to replace the cyclic lactam, we would expect Spark to come up with the immediately obvious replacements, 5-membered heterocycles. So for example, valdecoxib is one of the first results that comes up, and as medicinal chemists, this is something that they would expect to see. We'd also expect the less obvious but still obvious results, so for example, pyridyl in atoricoxib. But where the really interesting substitutions come into play are in the cases where cyclic lactam is replaced by sulfatriazole, and it turns out that this is a 12 nanomolar compound, and as chemists, not very many of us would scribble this sulfatriazole as a bioisostere for cyclic lactam. So using Spark, we can really get an unbiased list of bioisosteric ideas that we can try. To do a Spark experiment, the approach is simply to circle the bit of the molecule that you want to replace. The software records the distance between the attachment points as well as the angle. Conformationally populated fragment databases are then searched for fragments that have the correct number of attachment points and correct geometry. In this case, the byte size of the fragment is too large. In the next case, the byte angle is wrong. Hopefully, we'll find a good number of fragments that fit. Spark then forms the product and does a quick minimization to the nearest local minima before scoring against the reference compound. In this case, we scored back against rofecoxib. However, you do have the option of scoring against other reference molecules. Scoring whole molecule to whole molecule allows us to circumvent fragment-to-fragment scoring limitations. As you can imagine, you may find a fragment that works well at the fragment level. However, when placed in the context of the whole molecule, the electrostatics may be altered such that activity is lost. Whole molecule scoring, underpinned by Cresset's Z force field, allows us to see neighbor group effects and the electronic influence between these groups. So if we look at the two structures that are shown here, rofecoxib in green and the sulfatriazole analog in gray, we see that there's some big changes in the field point pattern up around where we made the substitution. However, we also see some more subtle changes in the field point pattern down around the bottom end of the molecule, as well as out around this phenyl group. So we're seeing this the electronic influence, based on the substitution that's been made. So where do the fragments come from? To create our fragment databases, we fragment existing molecules from various sources. The molecules are fragmented at heteroatoms, carbonyls and thiols, bonds to rings, but core functional groups like amines and carboxylic acids are not broken up. All sets of connected pieces are generated subject to some heavy atom and molecular weight limits. Once the fragments are generated, they're conformationally populated. Within Spark, we include fragment libraries generated from commercially available compounds and place them in databases that are coded by how often the fragment appears. For example, very common, common, less common, etc. We also include fragment databases generated from Chembl, which is a scrape of literature sources, Vehicle, based on the Rings of the Future paper from 2009, and Zinc, which gives us our reagent pools. Finally, we have an optional module called the Spark Database Generator, which allows us to create custom fragment libraries from corporate collections, inventory systems, and more. There are a number of ways that we can tether the results of a Spark experiment to synthetic chemistry. First, in our experimental setup, we can control which atom types are acceptable at the connection points. Secondly, we can use reagents from selected reagent pools and rapidly search all R groups that could be introduced at a selected position. Finally, using our optional database generator module, we can create fragment databases that are derived from corporate compound registries or inventory systems, which links your available chemistry and to the reagents that are available on the shelf. Now, in preparation for our 2011 ACS presentation, we explored designing new p38 kinase inhibitors with Spark using a fragment growing protocol. We took two co-crystallized inhibitors, 3K3I and 3ROC, as starting points, and using our experiment, we grew the smaller 3K3I DFG out ligand into something bigger, using the 3ROC DFG in hinge flip ligand as a guide. To set up the experiment, we first needed to add a methyl group to the ortho position on the tetrahydroisoquinoline part of the 3K3I ligand, and this serves as an attachment point where we grow our fragment from. Using Spark's ability to have multiple references to score against, we weighted the 3Ki ligand at 20% and the 3ROC ligand at 80%. And this is really because we wanted to push the fragments onto the field point pattern that is created by this 3ROC ligand. Now for this experiment in 2011, we did not use protein excluded volume. In the initial fragment growing results, our Spark results included structures that were very similar to a COPD compound that Pfizer deposited in the PDB a few months later. And this gave us confidence that our fragment growing protocol could indeed provide insight and power for our design efforts. So recently, we decided to redo the experiment. And in this case, we used Pfizer's 2-YIS protein as an excluded volume. And we looked to exploit the synthetic chemistry that Pfizer used to make their compound. For this fragment growing experiment, instead of using all of the commercially available compounds in our libraries, we chose to use Cresset reagent databases. And in this case, we looked at using the zinc database of commercially available thiols. And this should give us results that are readily synthesizable using the schemes that Pfizer came up with. When you launch Spark, a wizard launches that'll help guide you through your experiment. In the first wizard panel, we are asked to provide structures for starter and reference. The starter is the molecule we will make changes to, while the reference is another molecule that we will use in the final scoring. In our case, the starter is the methylated 3K3I ligand, and the reference is the 3ROC ligand. I have these structures stored in an SD file, so let's browse and get those from there. So now in this next panel, we need to choose which molecule is the starter. So let's ensure that our 3K3I ligand is the starter, and it is. And we also want to modify the weights so that 20% of the score is going to come from the starter and 80% of the score is going to come from the reference. Let's press OK. In this next panel, we circle the bit that we want to replace. So we're going to select the methyl group that we added as the point for our fragment growing experiment. In this next panel, we have the ability to control what atom types we're willing to accept at this connection point. Now we're going to do this control using a specific reagent database, so we'll just leave all of these checked for now. In this next panel, we have the option to bring in a protein as an excluded volume. Well, the protein we want to bring in is Pfizer's 2-YIS protein, and I have this saved as an empty Z file, and we'll bring that in. And that is it for the initial experiment setup. In this next panel, we need to select which fragment database or databases we're going to use for our experiment. Since we are looking to exploit synthetic chemistry that Pfizer used, we're going to select the thiols from the Cresset reagent pools. We'll turn the other fragment databases off. And we press Next. So that's our initial setup. Now with a fragment growing experiment, we don't want to restrict the size of the fragments that we're willing to accept. So I hit the Options button here, and I'm going to the Size Criteria tab, and I'm turning off this automatic constraint of fragment size. In some cases, you may also want to increase the number of heavy atoms that you're willing to accept in the fragment, as well as the molecular weight. Now we can press Go. So this run takes about 5 minutes. I'm not going to make you wait for this to finish. I've actually previously run this experiment, so we'll cancel this for now, and I'll open up the file of results. Okay. Now if we turn off the protein, so let's turn this around so we can take a look. So if you remember, this sulfur that's here was our initial methyl group that we used to grow the fragment from. So if we turn off our protein and we show the references, we'll see that the first result shows a fragment growing towards the 3ROC ligand, which is shown in that kind of pretty seafoam green color. We'll turn that back on. We can also view the interactions between protein and ligand by clicking this last button on the right-hand button bar. And this will turn on the interactions, hydrogen bond interactions, as well as steric clashes between the protein and the ligand. I already have mine turned on. So what we're seeing here is that this fragment that grew, we're taking advantage of some hydrogen bond contacts up in the hinge area of the p38 kinase. So as we scroll down the results, we see that our first couple of results have fused heterocycles. And then we have some where the heterocycles, the aromatic rings, are split. So we can visually inspect the first few of these. Now, in looking at these first few results, we see that the new fragments are structurally quite different from the reference compound 3ROC, and that can possibly help us look into new intellectual property space. Also within the results window, we have a radial plot. This graphically shows how, for a given compound, certain properties relate to each other. It's a great way to visually assess whether the results are in what you would define to be your sweet spot for design. If we double-click on the radial plot, we can take a closer look. In our case, we have two-dimensional similarity, topological polar surface area, S log P, bioisostere factor %, and molecular weight plotted together. Visualizing these values simultaneously is much more convenient and enjoyable than looking at lists of numbers. Now, this plot is customizable to whatever parameters that you would like to have in your table. For example, you can set your variables and your upper and lower bounds. And in some cases, users set their radial properties so that a large area encapsulated by the green means that we're in a favorable or a drug-like environment for their design experiment. So as we're going through the results, we may decide that some of these are really good and we want to share them with our colleagues. And we can select those as favorites. And I'm selecting these as favorites by clicking on the little star in the table. You can also add favorites by pressing the space bar. Once we've got some favorites selected, we can export those to an SD file, and they can be shared with our colleagues for discussion and for decision making on where to go next. Now, I've taken a couple of the interesting results from this experiment and put them in a pretty picture, which I've copied and pasted from Spark into my presentation. Let's go back there and we'll take a look. So looking at a few results from our Spark experiment, on the left, we have our Pfizer compound in the 2YIS pocket. On the right, we have result number 1 from our Spark experiment, which shows a nice fit into the kinase pocket. If we look closely at the thiazolo-triazole moiety, we see that it's taking advantage of the same hydrogen bond interactions as the Pfizer ligand. There are faint green lines there that we saw when we turned that toggle on in the Spark 3D window. So we see 2 hydrogen bond interactions here, and we see 1 on the Pfizer ligand. Looking at a couple more results that we found interesting, again, we have a nice fit into the pocket. We're showing fragments with hydrogen bonds, again, in that hinge region of the p38 kinase. Now, having used our thiols reagent pool, the same chemical transformations used to make the Pfizer compound could be applicable. We could also expand the reagent pool selection to include amines and alcohols, which might give some interesting results. However, it may involve the use of different chemical transformations in order to synthesize. In conclusion, using Spark's reagent databases can help quick profiling of accessible chemistry around a specific core. The optional Spark database generator enables creation of fragment reagent databases that are more tightly linked to your immediately available reagents. So, for example, your inventory system. So that concludes our webinar content for today. We appreciate your taking the time to attend and hope you will be able to join us for future webinars. If you would like to take a free 30-day evaluation of Spark, please contact us at inquiries@cresset-group.com, or you can download a trial directly from our website. Now, before we open the floor to questions, I'd also like to bring to your attention our next webinar, which will take place on May 27th, and will cover using our Blaze virtual screening as a software as a service via the cloud. We also have a European and North American user meetings coming up in June. These are open to users and non-users alike, and we hope that some of you may be able to register and attend. More details, again, are available on our website, cressetgroup.com/events. I hope we've been able to keep up with your questions as they were submitted, but if not, we will provide answers after the session via the email which you used to register for the webinar. In the meantime, should you have any questions, please don't hesitate to reach out to support@cresset-group.com. Now I'm pleased to open the floor for questions.